gentlemen, thank you very much for the opportunity to tell you about my overextended life story. And thank you, Madam President, for the invitation to come and talk to your society, of which I was once the honorary president myself a couple of years ago. Well, not a couple. And it's very nice to be here, and I want to start off by thanking everybody that's been kind to me over a long period. My young colleagues in the group in which I now work, who help me, particularly when it comes to, say, lifting out a wincher of chloroform, which weighs, after all, 5 kilograms, and my previous students, my colleagues in the department, and people who've been kind to me, and the technical staff here, for example, have been extremely kind to, you know, the old fart who comes and wants to do chemistry when he's finished teaching, and I much appreciate that. And the University of Sheffield has been extremely generous in supporting the research that we did when I first came here. Okay, so let me start this overextended journey. I was at a boys' public boarding school in Edinburgh, and it was just horrific. I didn't learn a thing except how to endure. So I can endure anything, all right? And sometimes you have to. I mean, for example, when our vacuum system in the lab doesn't work this afternoon. And to come to my first university, the University of St Andrews, and it was marvellous to be there. There were under 1,000 students when I went up in '48, and the lab was just there, and I lived in the hall of residence just there. You can hardly see the difference between them. And here you can see the West Sands, along which the opening sequence of the film Chariots of Fire was filmed, when they ran along the beach. Well, that was the beach they ran along. Okay. Now, this is the Wilgrot-Kindler reaction, which will be immediately familiar to you, though mechanistically I think it's quite a challenge. Anyway, we had projects, and that was my project. Everyone remembers their projects. Well, most people remember them, and that was my project. I can't remember what I was trying to find out, but probably variations in the structure. But it's an old reaction, and it's quite a sophisticated one there to go functionalizing that methyl group. Okay, just to put this in context, first of all, I had to pass a German exam before I could take my degree, because at that time, half of the world's literature was in German, and I'd never learnt any German. I'm hopeless at languages anyway. And I went to a German class run by an elderly lady who told us in German to get up and open the window. You know, that's not very useful for translating German papers, but fortunately there was available this marvellous dictionary which was composed by Mr. Patterson. So it's Patterson's German-English Dictionary for Chemists, and any word that appears in a paper in German is in the dictionary. So you can look up werden, for example, the past participle of to be, and it's there. And so all you had to do, I mean, I just learnt to string the words in the dictionary together and look up the dictionary fast and string them together and get the sense. So that was that. And the other thing, which I'll come back to, is the fact that instrumentation in chemistry hadn't been invented. So we didn't have any NMR, we didn't have any infrared, and we didn't have any mass spectra. Okay, so when it came to actually finding out what a compound was, we had to degrade it, and that took ages. I'll come back to that point later because it keeps recurring. Okay, and then when I'd taken my degree, there was a very kind man on the staff in St Andrews, Charles Horrocks, and he said, don't stay in St Andrews. If you want to do research, go down to London and work with my former supervisor, Donald Hay at King's College. So down to King's College I went, and that's what it looked like in those days. And the topic, it was an interesting little bit of competitive chemistry here, because if you take nitrobenzene and you nitrate it, then that's the isomer ratio that you get, 80%, 88% meta. But just down, and that was at University College, and that was C.K. Ingold, of course, who taught us organic chemists how to think. But down the road was Donald Hay, and he had found out earlier that if you, under certain conditions, for example, if you decompose benzoyl peroxide, then what you get is nitrobiphenyls, and you get a completely different isomer ratio. And this was the evidence that, of course, he was dealing with the radicals in solution and not a heterolytic process. And so he said to me, I want you to work on new sources of phenyl radicals. So being terribly obedient, I did that, and this is slightly unusual chemistry. If you take lead tetraacetate and just heat it with benzoic acid, you come out with the tetrabenzoate, and if you heat that in solution, it decomposes to give phenyl radicals. And you could tell that by the isomer ratios which you got from nitrobenzene. Similarly, another one, slightly unusual chemistry, if you take iodobenzene, oxidize it to the iodosobenzene, and then acylate it, then when you heat this iodosobenzene diacetate, you get benzoyl oxyradical as above and a phenyl radical. So that all worked perfectly well. Okay, and that was the only instrumentation that we had in the lab at that time. This is the Unicam SB500 UV spectrometer. And I remember it being delivered to the lab, and we thought, wow, what a marvelous piece of machinery. You could actually take the UV spectra. But here is the spectra. I've just scanned this straight out of my thesis. These look nice smooth curves. Each of these is an experimental point. You had to take a null, you had to make a null measurement with each point. And so to take those spectra would take most of a day. All right, we can now do it in what? 10 seconds or so, and that's a slight difference. Okay, right, now why should I show a picture of Stirling? And you see, it's all right for you people. You've grown up in peace and comfort. But in 1953, the Cold War was freezing, absolutely freezing, and the government was actually very anxious about the situation, and they were worried that the Russians were going to bomb us with chemical weapons. And so what they did was to set up a number of fellowships. When, at that time, when you graduated, all males between the age of 18 and 26 had to register for national service, conscript. And I didn't particularly want to go on the barrack square. And so I looked around for a deferred job, and there was one important type of deferred job, and that was with ICI Ardea, the explosives division. And they sent down on the milk round to King's College a couple of men, and I was shown in to be interviewed. And there was one there in a very, very smooth suit. And he said, I am the personnel director. And this is my colleague. He was sitting down, and people don't believe that it is true. He had a patch over one eye and his arm in a sling. He said, this is the research director. So I thought, I don't want to go to Ardea. So I put in for a civil service research fellowship. And the government had these very good fellowships where you could work on anything you like, provided it was within the interests of a research station. And I looked around the research stations, and one was Harwell, the atomic energy, and I didn't want to do atomic energy. But the Chemical Defence Experimental Establishment, that's the that's news speak for chemical warfare at Porton Down near Salisbury. And this actually was an extremely formative part of my career. And I was interviewed by the chief civil service interviewer, whose name was Harry Hoff, but he actually wrote novels under the name of William Cooper, and they're well worth reading. One of them was called The Ever Interesting Topic, and that was about sex in a boys' school. But anyway, before I had sat down, he said, "I hope you're not going to tell us that your interests are walking in photography, because we've heard nothing but that all morning." And I said, "Well, actually, I like carpentry." He said, "Why are you being apologetic about carpentry? Our Lord was a carpenter." And I said, "Well, he may have been forced into it." Anyway, I got a fellowship and went to Porton Down, and I worked in the little lab just there. It was lovely, because we were of officer rank, and we were waited on in the officers' mess by the national servicemen, of one of whom I might well have been. Anyway, the director then said, "We're very glad to have you with us," of course he had to say that, "and what would you like to work on?" And I said, "I don't want to kill people." And there was a horrid silence. And he said, "That's our trade." And I said, have you thought of working on the antidote to nerve gases?" "What a good idea," he said. Thank goodness. And so this is the work at Porton. Now, it's a little bit hard to appreciate this, but there were two chemists working in ICI, and they were working on new insecticides. And they had come across this phosphorus-containing insecticide, and they wrote to the Ministry of Supply in charge of the labs at Porton and said, "We've discovered material which is too toxic for us to handle. We don't want to do anything more with it. It's far too toxic. Would you like it?" So the Ministry of Supply said, "Oh, yes, please." And so, it's not a joke. These things, the reagents, they had LD50s, in other words, they would kill half of an experimental population with a dose rate of 0.1 milligrams per kilogram. And so 7 milligrams would kill a 75 kilogram person like me. And they were horrendously toxic. But, and it's interesting, every year I go to the safety lecture, and everybody I notice, all my young colleagues, wear gloves all the time. I never wear gloves, because at Porton we never wore gloves, because of the problem that if there was any defect in a glove, then the reagent would leak in there and spread over your hand and kill you for sure. And so the chemistry that I did turned out to be very interesting. I thought, well, the simple thing to do is work first of all on model compounds, non-toxic, and treat them with if you were going to decontaminate, you need very cheap stuff. And chlorine was an obvious one, of course, it was going to react with the sulfur atom. And so I was able to delineate this really quite long sequence of sulfur-containing compounds, things like sulfenic acids, sulfenyl chlorides. These were hardly known in 1955. They're much more familiar now, and odd little things like this sulfenyl trichloride and so on. And this was a lovely start for me in independent work. And that's what I would say to anybody who's going on with chemistry after their PhD. Do something different, because you need to be sort of jerked out of what you've been doing for the last 3 years. Okay. And this safety problem they realized that there was a danger of contamination with these very toxic compounds. And so we didn't have gloves. Instead, along the benches were self-inject ampoules of atropine. And so if you're contaminated, you just took one of them, stuck it in your thigh, and hoped you were going to survive. And atropine, the nerve gases, of course, are muscle contractors, and atropine is a relaxant. So that's the antidote. And there's atropine, and it comes from Atropa belladonna, the beautiful lady. Oh. Right. And then from Porton, I went on an ICI fellowship to Edinburgh. And the problem at that time was I really wanted to go into academia, but there weren't any jobs. And so I thought, well, the thing to do is to try and stay in academia. And the ICI Edinburgh, I got the fellowship, and I said, oh, I'll have it in Edinburgh. It's a good department then, and it still is. And this was an opportunity for completely independent work. And I worked on this reaction, and one does stupid things. It looks like a nice, simple reaction. It's interesting because it's the oxygen atom of the amido group that's the nucleophile. Provided you keep it neutral, you then come out with the iminofuran instead of the cyclization which goes through the nucleophilic nitrogen. And I'm just trying to conjure up the primitive nature of our labs. We didn't have rotary evaporators and things like that. We had water baths, okay, and you had concentric rings on the top of the water bath, and I had made the compound, and it was a low melting solid. So I put it on a watch glass, and being bone idle, I just put it on the little hole in the water bath. And when I turned around, it had melted. And so, you know, a few rude words do escape one under these conditions. But the amazing thing was that it melted, and then it re-solidified. Yes, and that's nice. I like that sort of phenomenon. What was happening, of course, this was cyclizing through the oxygen atom to give the salt of this compound. So no wonder it was a higher melting solid. Okay. What else did we do? Oh yes, now do you remember about slides? Do you remember 2x2 slides? Let me take your mind back another 50 years. And slides, it was a different matter. There is this, I put a picture up in case it couldn't be seen. There's my slide describing this work at a colloquium in Edinburgh. And there's the slide. I kept the slide. Okay. Now, what you did was you took a sheet of glass and you wrote the chemistry on it, and then you put, with felt tip pen, and then you put another sheet of glass on top of that and bound it around the edge. And then you had to put it into a projector, and the light in the projector was a carbon arc. Okay, and so you had these two electrodes and you moved them together gradually until they struck, and you got lovely bright light. And I remember in my colloquium, you had to have a little curtain at the back of the projector so that you could see what you were doing, and the curtain went on fire. And that doesn't happen in every, at least I don't think it's going to happen tonight. Anyway, the curtain went on fire, so much fuss with the extinguishers and so on. But things have moved on a little bit into the digital age. Thank goodness for PowerPoint. Right, what a load of nonsense. Okay, yes, so that's the salt. That was the salt that was solidifying. Okay, and then from there, again, I got into academia. And you see, these days, I mean, you have all sorts of internal promotions and so on. But I had a very rough career. I had to compete for every blinking job that I ever had, except this one. And so I went to Queen's Belfast. This is the David Keir building, where the chemistry department was located. And I had an office, and off my office was my own lab. It was a perfect start to an academic career. And we didn't have any nonsense like tutorials and things like that, wasting our time. So once we'd given our lectures, we could just do our own experiments, and that was lovely. And I worked then on, again, slightly curious chemistry, very simple, because all the chemistry that I'm capable of doing has to be very simple. Okay, so making cell phones, acetylenic cell phones, like very easy, you see, you just take a thiol and propargyl bromide, you've got it. But if you put it down in an alumina column, it isomerizes, and it isomerizes to the allene, which is the thermodynamically stable isomer, and that's unexpected. Allenes on the whole are of higher energy than the external or the internal isomer. And also they undergo nucleophilic addition, and so you get these functionalized adducts. And quite a lot of chemistry's been done on that system, fortunately, by other people. I don't want to put down synthesis or anything in any way, of course, not in the slightest. And the other little thing was isotopic asymmetry. I thought it would be interesting to see if we would make a cell phone optically active by the reason of having isotopically different oxygen atoms. This had been done already with deuterium, but this was the second example. And my friend Ken Anderson had already shown that if you treat a methyl sulfonate, all right, one enantiomer, treated with, I've left out magnesium, benzyl magnesium, you come out with the sulfoxide optically pure. Okay? Now I thought if we take an optically pure sulfoxide and oxidize it, we might get an optically pure sulfone, right? Then how do you do that? What reagent do you use? Well, the obvious reagent used is hydrogen peroxide in acetic acid, so it's peracetic acid essentially. But then all you have to do, as they say, is to make hydrogen peroxide with O18s. Okay, now again I want to take you back in your minds. We're now in 1963. Where do you get O18 from? And the only country that sold it was Israel. And so I went to my head of department and I said, I wonder if it'd be all right if I buy some O18. How much do they cost? I said, £100 for 100 ml of O18. He said, that's ridiculous. Anyway, my organic chief, Bernard Henbest, backed me up. And so they delivered from Israel 100 ml of O18 in a glass tube. You're not sure if you're getting anything, that's the trouble. Anyway, we connected this up and I thought, okay, well, the reaction with sodium is going to go like a bomb. Oh no, it isn't. To get sodium to react with oxygen, I had to blow it to the inside of a flask, so a sodium mirror, and then emit oxygen, and then heat it 200 degrees to get it to react, and then wash it out with acetic acid. And we got the cell phone. And here's another problem for people. It's when you make a measurement, be very careful that your desire about the result of that measurement is not affecting the measurement itself. Okay, and the specific rotation that I could measure was somewhere between 0.1 and 0.2 of a degree. You know, it's damn all. But fortunately, and the polarimeter we had in Belfast was very primitive, but fortunately I could send it to Oxford, and they had an electronic one, and they measured this rotation accurately. Okay, we actually did this again with carbon in another situation where we had dibenzyl sulfoxide with two different carbon atoms. That's another story which I won't tell you. Okay, so then after that, I put in for the readership at King's College. This is what it now looks like. This, of course, is Somerset House, and that bit is King's College. Over the wall there is the old King's College. And again, it was a competition job. I put in for the readership, which was the only readership in the country advertised. So I put in, and it was offered to Carl Overton, Glasgow, and fortunately he withdrew. And so I had the readership, and we then worked away, and I had a very, very good student, Chris Knight, who came with me from Belfast. And I said, why don't we look at inductive effects on elimination reactions. Very simple question. If you move the removed proton away, how does that affect the rate? Well, what he found was you don't get, in certain cases, you don't get elimination, you get cyclization. Now, of course, at that time, we knew all about cyclization because Rutziker in Switzerland had defined the rules for cyclization. 6 was going to be the best number because it's strainless ring. It's all rubbish. And we found, in fact, that as a function of the ring size here, these are the relative rates, and which is the best, by far is the best, is the 3-membered ring, the most strained of all. 1,000,000 times faster than the formation of the 6-membered ring. Okay. And the 4-membered ring with the same strain, virtually, is 10 to the 5th times slower. So there are obviously little things to follow up there, little questions. Apparently, these very simple systems are nevertheless profound in their content about a question like that. Okay. And then we also worked on activated eliminations of this sort, and this work was done by John Crosby. And the important part of this work, from our point of view, was that if you choose the mechanism of the reaction right, which is determined by the nature of the group X, then you can, if you have an intermediate carbanion, then you can measure the rate at which the carbanion loses the group Z. So that enables you to measure leaving group abilities. Now that's a very tense little pedagogical subject, because you may possibly have been told by your teachers that leaving group ability is directly related to the acidity of the conjugate acid of the leaving group. I hate to worry you, ladies and gentlemen, but that's rubbish. Okay. And I'm going to show you that. So, after we'd worked there, this was my next competition. I was now 38 years old, feeling my age, and I thought I ought to compete for a chair. And so I competed for a chair at Calixarenes, and a colleague in Belfast got that chair, and well done to. He was just the right man to be the foundation organic chemist at Calixarenes. And then I competed for one at Lancaster, and that was an internal appointment of a chap who was fortunately faded from consideration. And so I put in for Bangor, and Gordon Whittam, that some people will know from Oxford, he was offered the chair, but I think his wife put pressure on him, and he withdrew, leaving me as the Professor of Organic Chemistry in Bangor. Okay. Now, I mentioned this business of leaving group abilities. Of course, people talk about leaving group abilities in a process like nucleophilic substitution. That's a load of rubbish, because your nucleophile is going to interact with your leaving group anyway, and you can't quantify that, so forget it. Okay. But you can do it in elimination reactions, because as I mentioned before, you form this carbanion, and you can actually measure how easily the group Z comes off. And here's our table of leaving group ranks. That's just a fancy word for ability, really. And work done by Patsy and Richard, and covering a nice wide range of reactivity. All physical organic chemists want to have big ranges of reactivity. Factors of 2 and 10, forget it. And I used to start lectures by saying, the only valuable ratio that you should start off with is 10 to the 3 at least. We've got a lot more than that here. The best leaving group we studied is phenylselenide with a rank of 10.4 log scale, and the worst was malonate. Okay, so we're covering 13, 14 powers of 10. Huge differences in reactivity. Okay, now I'm not going to go through that list, but I just want to leave you with one problem to which I do not have a solution, and I look forward to having that after the lecture, and that is, if you compare cyanide and phenoxide, right? They are the conjugate bases of acids with identical pKa's in water, yes. And their leaving group abilities are at least 10 log units different. Why is that? Why is cyanide such a terrible leaving group? I just throw that in the air and go quickly on to my next slide. And then we also wondered, okay, we know about leaving groups. Can we strain the bond to a leaving group and see if that affects leaving group reactivity? In other words, of course, first year student in Sheffield would know perfectly well that if you take ethyl, methyl, ether and treat it with a nucleophile, it won't do anything. But if we strain the bond, then of course the reaction of nucleophiles with ethylene oxide is perfectly familiar, and it's done without any hesitation or thought about the mechanism probably. Okay, but how much? So we set up just one example here. Here's our cell phone with a carbon leaving group, treated with the base, and it gives the carbon leaving group, KREL1. We like KRELs in physical organic chemistry, but if you just strain that bond by incorporating a 3-membered ring, you get an acceleration of about 10 to the 11th. And again, that's worth having. And then, of course, it raises the question, well, okay, how much of the strain of that ring is being expressed in the enhanced reactivity? And we can calculate that. And it's about 50% of the ring strain is expressed in that process. Work done by Simon Hughes, and I actually talked about that at a Chef Stereo symposium here in about 82 or 3. Okay, and then, oh yes, then I had a nice thing. This is the red box. I had this red box in the post, and in the red box was the certificate of my election to the Royal Society. And you would think, oh, they'd be congratulatory and welcome and so on and so on. Yeah? Not a bit of it. Look at this. I think it's disgraceful. Upon cause shown to either of them, that's not turning up on the right day, your election will be void. Yes, that's the kindly welcome that you get. And incidentally, when you are elected to the Royal Society, you sign the charter book. And that is one of the big thrills that I've ever had in my life, because you're signing the same book that has been signed by Christopher Wren, by Robert Boyle, by Charles Darwin, and so on. It is a thrill. But be sure that you don't sign your name below someone famous. And there's an example of that here. This is, the charter book has been produced reproduced in a Xerox form, and here's a signature, you see, which has nearly been rubbed out, and it follows this guy, I. Newton. And so be careful about that. Okay. And then, for once, I didn't have to compete for this job, and that was nice. They said, would you like to come? I said, no. And my wife certainly doesn't want to come. So we thought about that and then we came. Anyway, that's what the building looked like then. Okay. And there was a nice situation here. I said, look, I was being asked to come within 3 months of my 60th birthday. I said, look, I've got to have a reasonable tenure. Make it 8 years and I'll come. They said, okay. And in each of the 8 years of my tenure, with my organic colleagues, we were able to make appointments of terrific organic chemists. They were terrific. They are all 8 of them. I was able to do 1 a year for 8 years, and all 8 of them are now professors. 1 is, you see, quietly blushing in the audience here, and 2 of them are fellows of the Royal Society. So I don't think we could have done better, frankly. We did have slightly unusual recruitment techniques, but nevertheless, when I had my first job in Queen's Belfast, I was interviewed for 15 minutes by the Vice-Chancellor and the two professors in the department, and they said, "Good afternoon, Dr. Stirling." We didn't do that, did we? Yeah. No, we did not, and that's why we got good people. Right. And one of these was a bright lad, and by the name of Williams, and he was the closest to me in terms of interest in the discipline, and he'll recur. Okay. And we had got into surface work in Bangor. We were just starting, having been nagged by some physical chemists and engineers. And when Victor joined me as a postdoc, he's now at York, and we said, why don't we look at the reactivity of ordered films? Because it's physical organic chemistry in a slightly different way. And if you place the right sort of molecule close together on a surface like that, and compare it with a corresponding surface where you haven't got these groups which are going to be reacting so close together, is there any difference? And the answer to that is kinetically, yes. This is a simple first order loss of the starting material. But here it's sigmoid. In other words, you start very slowly and then get faster and tail off again. And the reason for that is we concluded, and we collaborated with a lab in Holland, and because you only get reaction in the gaps, and so you've got very few gaps to start with, and then the gaps get bigger, and then the reaction goes normally. The analog that I would put to that would be, you know, packing cars on a cargo ship. Very low ordered, highly ordered, but with a few gaps there in which reaction can occur. Okay, so the kinetics fit the physical structure. Okay. And then we started to work on Calixarenes. And they get their name from these Greek vases. Okay. And so that's a typical Calixarene molecule. And what they consist of is a bowl, all right, surrounded by hydroxyl groups and on legs. And the structure of the leg can be very variable. I think I've got the chemistry of that. Fortunately, they're easy to make. Otherwise, we wouldn't be working on them. Yes, they're very easy to make. You simply take either resorcinol or pyrogalol, treat it with an aldehyde and a bit of acid, and you get stuff. And it was Frank Davis who worked with me on this for a long time. He was postdoc with me for half a dozen years. Very imaginative lad. Only problem is he didn't like cleaning his teeth. That may sound a little bit odd, but they were green. And I always found that a little bit sort of anxiety making. Anyway, he was, you don't work with people with green teeth, do you? But honestly, anyway, Frank was very imaginative. And he kept putting his head round my door and saying, have you thought of that? And have you thought of that? And I never had. So he can have his green teeth. He's welcome to them because he was very good. Anyway, one of the things that we investigated was the structure of these with long chains. Here's the crystal structure done by Harry. And it's best illustrated, I think, with this one. You've got these long chains, but this crystal structure shows that in the solid, they interdigitate like crazy. So that's another chain going up there, okay, and you get these multi-layers. Here they are, I hope, yes. So if you anchor a calixarene, and those used to surface chemistry will recognize the sulfur gold layer, but then if you put another one on top, it sits on top, because these are very, very hydrogen bonding here, so they're very hydrophilic, and you form the multi-layer. And you can tell you're getting multi-layer because you get a big change in the contact angle. going from a low contact angle here of about 20 to one of about 90 there. And also you get a huge change in the CH stretching intensity because you've got far more hydrocarbon. But then the question arises, well, why shouldn't you get an infinite number of layers? All right? What is stopping it? Well, the analogy that I would have would be a meeting of bishops with the Pope. And you see the ones in the front row here are all very well behaved and very well ordered. But in the back row, you see they're starting to chat and misbehave, as people do at the back of lecture. And I think it's the disorder at the surface of a multi-layer which is preventing successive deposition. Okay, well, if you believe that, you believe anything. There's a drop of water on a slide, and I just want to talk about contact angles for a second, because you can think, well, all this is purely academic. No, it isn't. There's contact, that's bifurcation. So that's the contact angle there is 19 degrees. Okay. Now, that's my wife's engagement ring with 3 micro diamonds, one there, one there, and one there. So I put a drop of water on the middle diamond, and you will see that the contact angle is not 19 degrees, it's about 60 degrees. So you can, ladies in particular, when you're buying rings, just take a little container of water and a dropper with you and check, just by putting a drop of water on the diamond, if you're buying diamonds, and just check the contact angle. Okay, and if it's low, reject it. If it's high, buy it, but insist on getting a discount from the jeweler because he'll be very impressed with your technical expertise. Okay, now, if you look at these molecules, let's take this. We've got hydrocarbon legs here, and we've got a very, some to pieces too, you've got a very, very hydrophilic surround here. So supposing that's a hydrophilic surface, that is going to bond there very easily, and now you've changed the nature of that surface because you've changed it from being hydrophilic to being greasy and hydrophobic, yes? And so we thought, well, okay, we'll examine these molecules to see if they'll change the nature of surfaces. And they do, in actually a very practical way. So there, see that line there, separates untreated wood from wood treated with of this molecule, about a 0.5% solution. And there's the drop of water with a lovely high contact angle. Okay, and this is the sort of stupid experiment that one does in this situation. Here are 2 lumps of sugar. One of them has been treated with a calixarene and the other hasn't. And after 4 minutes and 32 seconds, there is the untreated lump and there's the treated lump. Okay, so this is a very simple way, of course, of dietary control, obesity control. You've just, all your sugar lumps should be treated with calixarene. There's a slight problem because it doesn't make coffee taste very sweet. Okay, but this is the one I think that I'm proudest of. Here is a ball of cotton wool treated with the calixarene, so making it hydrophobic. So it floats on water, but the little drop on the top, and it's this fluorocalixarene, the little drop on the top is of liquid paraffin. So you're preventing both oil and water attacking this surface. Okay. And then the department was refurbed. Okay. And I had come to the end of my tenure, and I needed a supervisor. Okay. And so again, just thinking of the closest nature of the work being done, that's my supervisor. So he took on the control of this student, and the very first thing that we thought we would look at would be carnivorous plants. What's the problem? Well, if you're an ant, you can walk all over this. This is actually called the pitcher plant. You can walk all over it, provided it's dry. But if it rains, keep away from a pitcher plant because you'll fall in and you'll become the pitcher plant's lunch. Okay? And then what then, of course, at the molecular level, what's happening? Well, this phenomenon was first investigated by Julia Eisenberg at Harvard, and one of her investigations of the surface was to allow a carpenter ant. I mean, you know, here we have it. It makes Professor Harity look friendly, but, and she allowed a carpenter ant to walk across her surfaces. And we had done, and I'll show you the chemistry in a second, we had done related chemistry, and I went over to our insectary, and this is the sort of people that help you. Mike Siva-Jyoti is in charge of the insectary, and I said, could you lend me a carpenter ant? He said, what do you want it for? I said, all I want to do is to walk over my surface. And he said, you don't want a carpenter ant. Because they're trail animals. They'll only go on pheromone trails. What you want is a different insect. And I'll come to that in a moment. Okay, so the chemistry that we actually did was this. We took this perfluorocalixarene, put it on cloth, so that, of course, the fluorinated legs point up in the surface. And so we've completely changed the nature of that surface. And notice that perfluoro chains, by comparison with hydrocarbon chains, are extremely rigid. It's a very, very notable thing that comes out of the models. Okay, so what we did was to put a perfluoro compound on top of that. This had also been used by Julia Eisenberg. Krytox, perfluoropropylene oxide, and it's a curiously dense material. And then what we did, so that just to reimagine this, we've got cloth, we've got fluorocalixarene, and then on top of that we put Krytox, and then we test it out with hexadecane. And if you have the cloth alone, rapid absorption, here's the control experiment, rapid absorption, just the pyrogalline by itself, rapid absorption, neat Krytox, rapid absorption, neat Krytox, and then F-pyrogalline, rapid absorption. But if you put the pyrogalline on first and then the Krytox, the hexadecane doesn't soak in. Okay? No absorption in 10 days. And so we've profoundly changed the nature of that two-layer surface. And, oh, there's my actual experimental thing. You notice it's test number 105, and rather crudely cut with the scissors. But here are the drops of hexadecane on this cloth, which is vertical. And so, of course, gravity is taking the drop shape, but it's not moving the drops. So there's something really, I think, quite profound about that. Okay, and the test insect, we tested our surfaces with this animal, which is the bed bug. And Mike Siva-Jyoti said, look, I'm only going to release to you sterilized male bed bugs. If a female gets out, there's hell to pay. All right, and so it's a two-layer coating with rigidity. Right, and then this is just a reminder of the fact that we get deep interdigitation of these hydrocarbon legs. And also, these calixarenes can exist as hexamers in balls. Okay. And then I thought very naively, and this is the level of my thinking, very simple. Okay, if we take a calixarene, will it absorb a long chain hydrocarbon? We need to be able to see that, and we can do that by putting a double bond in there, and then we can see it in the NMR. Great. Very, very simple. And so here's the solution. which is quite difficult to make of the calixarenes in octene itself, so I just heated it briefly, and when you heat it, you get that. And when you cool it, you get that. Now, I had been brought up at St Andrews to believe that when you take a solid and you put it in a solvent and you heat it, the solid goes into solution, and then when you cool it, if you're lucky, it comes out again. This is exactly the reverse. What, what on earth is happening? Okay, and what is happening, and I won't bore you with the long tail, the hexamer and the layer structure are in equilibrium, but the white stuff coming out is amorphous. And we can tell its size by using, I've had to learn a lot of techniques in my old age, quasi-elastic dynamic light scattering. And that shows that the amorphous material, the white material that was coming out when we heat the solution, those were lumps of molecules containing about 500 molecules and being about a micron wide. And that's the sort of thing that you can only, with good digital modern instrumentation, find out. Okay. And then, and I think this, yes, this brings me nearly to the end. This is a biliary stent, and you can see the scale of it. I apologize for the non-metric scale. And if you have carcinoma of the abdomen, then quite commonly the bile duct leading from your gallbladder to your duodenum becomes obstructed. And that means you can't digest fat. And that's very bad for the patient nutritionally and also for morale, because a lot of the flavor and taste of food goes in the fat content. And so the trouble with these stents, and I happened to be at dinner with a surgeon and we were exchanging what we did, and I said, we're working on coatings which are going to be protein resistant. And he said, well, that could be of interest to us. I'm taking a biliary stent, one of these, out of a patient tomorrow. Would you like to have it? I said, yes, please. And so he sent me in an envelope this revolting object, and here it is. And you can see what the problem is. Once that stent's been in a patient, the body behaves like a recruiting sergeant in the army. You know that, where the recruiting sergeant will say to the new recruit, if it moves, salute it. And if it doesn't move, paint it white. All right, and that's what the body does. It either rejects implants or it covers them with this awful muck, which is protein and cells, and blocks the holes, of course, with which the bile's got to come down. Okay. And we had invented this coating. We just put, in the simplest possible term, we just put peg legs onto our calixarenes. Makes them very protein resistant. But the problem, of course, is that things like stents have been manufactured to be non-stick. So how do you get to stick on a non-stick surface? Well, we have to go to the world champion sticker. All right? And the world champion sticker is a lot better than humans. It's been around for about 500 million years, Precambrian. And think of the number of experiments you can do in 500 million years. You get a PhD easily in there. Okay, anyway, the muscle sticks. And it can stick underwater. We can't. Okay, so here's the muscle, and it sticks with these little pads here. And each of those will bear a load of about 100 grams. And so a muscle is typically sticking to the pier with a force of about 2 kilograms. Okay, now here is a close-up of the pad, and this very, very technical looking thing is just mitulus edulis foot protein. That's all. Mitulus edulis. Isn't it awful? The edulis part of the biological name says edible. You can eat me. I think it's terrible. Anyway, it sticks on. And when you analyze that protein, it's 30% L-DOPA. All the Y's there are DOPA. Here's the polymer, and there's the molecule. Okay. And that's what is, so in our current work, we're trying to incorporate DOPA into our Calixarenes, which we know will stick, and we hope to get polymerization and hence adherence. Anyone who's thinking of working on DOPA and dopamine, think carefully. They're terrible molecules. Anyway, now, as I mentioned, you can make variations in the bowl, and we were interested, I'll just translate that, it means Professor Williams nagged me into getting 5 substitution there. Okay, and so, right, so now we're into synthesis. Okay, now for the physical organic chemist, of course, synthesis is just a drag. All we want is the molecule. We're not a bit interested in getting the thing. We want it preferably out of a bottle for 5p a kilogram. But okay. So we thought, okay, if we're going to get 5 substitution, perhaps we can plug in here. And we were aware of a molecule using SciFinder, and here it is. This is cytosporone E, and it's an antibiotic which has been extracted from a fungal infection of a mangrove swamp in Indonesia. Now, why on earth anyone wants to go to a mangrove swamp in Indonesia is beyond my comprehension. But anyway, that's where they got the stuff from. And then synthesizers say, right, we've got to make it. Okay, well, this is how they made it. I'm going to go through this quite quickly, as synthesizers do. Have you noticed that? You had a lecture. I can't even follow the acronyms, let alone the structure changes. But anyway, here you are. There's steps 1, 2, and 3. You don't need to worry about the details. There's steps 4, 5, and 6. You don't need to worry about the details. 7, 8. And at last, after 10 steps, we've got cytosporone E. Well, physical organic chemists don't have time for that nonsense. And so we just take pyrogal, gallic acid, treat it with octanol, HCl, and we get cytosporone E in 1 step, proved by X-ray structure, atoms. That's the sort of thing. So I'm not going to do synthesis. I'm going back to physical organic. Thank you very much.
Does anybody have any questions in particular they'd like to ask? If not, there will be a wine reception up in G14, and I'm sure that with much wine, more questions will flow a lot easier. It's up in G14 now after the lecture, so all that's left is to thank you for a very, very entertaining talk. And you didn't even use the pipette and the piece of tissue.
I forgot about that. I must. When I came back to the lab, people said, what are the major novelties that you find after all this time? And I said, forget instrumentation. The things that impress me are the laboratory tissue. These weren't invented when I was doing my PhD. And the disposable plastic graduated pipette. I mean, they're marvelous. We didn't have those. You don't know how lucky you are. Yeah.
So now that we're very grateful we have NMR and IR,
Yeah.
thank you very much for a very, very entertaining talk.